if you're trying to do data reference tracking, you're actually building a huge tree of references, and it's almost like rather than worrying about the actual value of what that is, you're worried about who's touched the same types of memory locations. So you end up emulating a lot of work and doing a lot of computation behind the scenes, and as you do that, it becomes closer to true emulation or execution as opposed to static analysis. So let's take a little deeper look at what types of information you should get from the basic disassembly analyzer. These are the functionalities that we already expect out of something like an IDA Pro or a more advanced disassembler. They should include things like function detection, static data references, string references, understanding execution branches and where a call came from or where a jump came from or where it's going to. That was very simple. It's, as long as it's using immediate values, 80% at least is pretty readily available to a disassembler that just has a little bit of logic for tying this stuff together. And then in addition, something that we don't see a lot of is disassemblers that have like advanced hinting for us, things where maybe it'll make comments about what it guesses a chunk of code does, or maybe it understands system headers like WinDebug, understands Windows objects very well, and you can output a structure format of anywhere in memory. Well, we don't really have a disassembler that can say, I understand that this is using this object and this is what it looks like, except for IDA. IDA is pretty good about understanding that this API call takes this data object and this is what it looks like as values are being passed to it. That should be a standard feature, though. It's not difficult to parse header files and understand the objects that are actually inside a compiled binary, if that information is available. And then things like on Unix system calls and all this information is static. It just simply needs to be collected and parsed and then just built into this like knowledge database that a disassembler already has. So function detection is one of the more basic analysis tasks. It's actually quite trivial. Basically, in most standard compiled binaries that include function prologues, there's a standard method of doing a function prologue. In the case of standard C, it's usually push EBP and move ESP to EBP. That's just basically storing your frames so that you have a new frame of reference for this function. When you push stack variables and whatnot, you're actually kind of closed off in your own local context. So that's what the purpose of a function prologue is. In some cases, it also does things like initializing stack canaries, or maybe if you have some function-based packer, it will do its packing and unpacking or encrypting in the function prologue as well. And Microsoft actually, in Visual Studio, has now modified the function prologue a little bit. I thought I'd point it out. They've added a move EDI in front of the push EBP and move ESP EBP, and they've also included 5 no-ops prior to the function prologue. And this is in all system libraries and system drivers for Windows. And basically what it allows you to do is it allows you to apply trampolines elegantly without having to overwrite a couple of bytes of the actual beginning of that function. So essentially, you would overwrite the move EDI with a jump backwards 5 bytes. And then in that jump backwards 5 bytes, a relative jump is actually 5 bytes as well. So you create a backwards jump and then a forwards jump to anywhere in the code that you want. That's a way to do a trampoline. But it's just that there's very standard prologues, so you can detect these in code. In the case where there aren't function prologues, where they omit the frame pointer and they don't keep frames, they base variable references off of the stack pointer rather than the frame pointer. You can just look at the call destination. So when we parse through code and we see that it's calling to a certain address in the code, well, a call means that it's going to push the stack pointer, or the current code location prior to making that call. So you're making a functional context switch. So you can treat those the same as a function that would have already had a frame initializer at the beginning as well. And in the case of a disassembler, if there's no symbolic name from a symbol table, then it's pretty standard to assign it something like sub underscore and the address of the code location. And later you can go back and rename that. But just initial understanding. And then here, this is actually some text that's taken from a disassembler I wrote. I'm going to be releasing that today. And it shows cross-references of where this function was being called from. And that's just, it makes for easy navigation and quick referencing within the code. Let's see. Oh, I believe I went backwards. Here we go. So as we build this database of where the functions are and where these code locations are, we begin to see these cross-references that are determined by examining the immediate or evaluated, immediate operand values, meaning like an actual static valid address, or an evaluated address if we're capable of following through a few instructions and we see that they've moved an address to a register and maybe they've added an offset to it or something. That's not overly complicated. But the point is that if you can understand the destination of a call, then you can create this cross-reference and these symbolic representations. And the one thing, though, that is required to actually track cross-referencing well is the inclusion of permissions flags within a disassembler instruction decoder. So these would be things that would signify this operand reads from the other operand, or this operand writes the other operand, since we don't really have to, or in that way we don't have to actually keep another table of, well, all adds work in this way, they read from one, write to the other, or all jumps work in this way, they execute operand one. So if you include these flags within that, it's easily parsed and makes for good cross-referencing well. There's only 2 libraries that I'm aware of that are open source and available you can use right now, one being libdasm, which is written by JT, who has his code posted on nologin.org, and then the other would be libdisassem by Mammon, which also includes a cross-referencing capability. And as you're parsing the operands for the cross-references that might be produced by each line of assembly, there's various types of operands, immediate, memory, and register, as well as displacement, et cetera. And depending on how complicated your operand evaluator is, if it can determine these relative offsets or not, you actualize that value to a memory address and then do your lookups based upon that. So there's basically code execution flow and data flow that we're going to be concerned with. Code execution flow is going to give us a graph of possible destinations within the code from various code blocks and what all the paths are through the code. And those can be determined through 3 basic assembly flow control instructions: calls, branches, and returns. And they can just be analyzed for functionality and creating this tree. As far as data associations, you're going to be looking more for the symbols, strings, and pointers within pre-initialized data. And if you get into emulation, then you can also look at pointers within heap allocated data or runtime allocated data as well. But you can see here, I have the cross-reference at the top is obviously a code cross-reference. In the 4th line there, the move shows from the address 402000. That's going to be the data section within a PE file. And so that just shows this is a pre-initialized string. We know what that is. We know it's a static offset. And then the next line is a call printf, which we have a symbolic name for since that's a shared library symbol. And finally, to get back to hinting, system call hinting is a pretty obvious one. We know the syntax of system calls. We know that most system calls take their arguments in the registers, which makes it pretty easy to determine what the register state is at the execution of an int 80. And it's a matter of parsing a simple kernel header file and just building, again, those structures within the database. And every time you hit an int 80, then you just look at register state and you determine which values have been passed into EAX, EBX, et cetera, and are able to enumerate the arguments to that system call. And then again, the parsing of default library header files and possible open source shared library include files as well. And then you can even go as far as doing something like kind of heuristic function call argument detection. I did this in DLTrace, which was a bit of a hack, but it was a dynamic shared library call tracer. And it basically analyzed a program in this method here to essentially determine at which offsets within a function it was referencing argument values that were passed and local variables that were passed. And then depending on the size of that reference, it would determine, is it referencing a word size value or a d word size value? Is it dereferencing it within the code? Is it a pointer? Does that pointer evaluate to something that points to ASCII data? Doing a simple, is it 4 bytes of ASCII text in a row? Well, if it is, why not show that at runtime as a string value. Well, this can be done very similarly on a static analysis point of view, where you can also simply analyze the arguments based upon their offsets from EBP or ESP, depending on if they're using frames, and determine how many arguments there are and how those arguments are being used within the program as well. And IDA represents this through naming arguments like arg0 through argn, whatever it may be. So, in my opinion, I think most of the features described here are fairly basic. It's mostly cross-referencing of known data. And there's only a few disassemblers available right now that do implement at least 4 out of 5 of these features, and that would be IDA, HTE, which is a great cross-platform visual console disassembler, the Bastard, which has gone through a couple of development phases. I think it's currently going through another rewrite, but quite powerful library. And then Codis, which is the tool that I wrote. And I'll give you a little demo here. It took me about 2 weeks or so, maybe 3 weeks, to kind of get this working to the stage that we have it now. And it's capable of parsing both PE and ELF. Let's see, I guess this is actually pretty small. All right, let me see what I can do about that. Is that a little sort of better? All right, we'll try it. So anyways, I have an ELF file and an exe file here. Codis has a few options. It's not like a super functional disassembler, but it can do AT&T and Intel format parsing, or format representation. It can show the hex bytes if you find that useful. It can dump symbols, only show the headers, etc. So we're going to go ahead and just check it out on an ELF file first. Is there any way we can fix this? I'm sorry?
Could you move the screen a bit to the right?
Yeah, they have it expanded a little bit. Here, let me see.
Can you maybe switch the light on?
Yeah, I'm fine if we want to dim the lights real quick. I don't know if that'll help here. Basically, it shows at the top here, it's detected 4 main sections that it's going to be dealing with here. As executable sections it's going to disassemble. The other ones it treats as data because in the section header, flags are set to only be readable and writable as opposed to executable. So that's a very simple way to determine if code is going to be executable. It reads the file header as an ELF, a 32-bit ELF file, which is little endian, and evaluates the entry point and the file size. And the first section in an ELF file is typically a null section, so that's why you see, or maybe don't see, it's actually getting brighter up here, I think. Okay, well, I hope maybe some of you can see this at least, but basically by default, Codis will provide a hex dump of data sections, as you can see here. And when it gets to an actual executable section, you will see that, here we go. This is the PLT section, which is where all your dynamic symbols right here on the left you can see are being resolved through the symbol table lookups and relocated. Of course, this is where most of your cross-references are going to be within the code for dynamic symbol calls, or dynamic function calls, rather. Let's see if I can find the text section. Okay, so and here's the text section. Same deal, cross-references, temporary names on detected functions. There should be some jump cross-references as well in here. Symbols obviously are being resolved. So it's a semi-useful console disassembler, but basically I wrote it